Hello everybody, thank you for joining me today. My name is Manam and today we're going to be looking at electrical power. So some of our learning objectives include to understand what electrical power actually is and to recall the two power equations. So P equals I times V, which is one, or P equals E over T, which is another, and to also understand the power safety features of a UK plug such as the fuse. Now let's start off by looking at what power actually is. Power actually has a very simple definition and it's just defined as the rate of transfer of electricity. That's it. So that can actually be shown very easily in the power equation. So P is equal to E divided by T. So let's have a look at all the units over here. So P power, which is in watts. This is also known as joules per second, but really the only thing you need to worry about is watts. E is energy. Energy has a base unit, which is joules. It's actually big E though, isn't it? So let's have that, and then let's have another, no, green, sorry. And then let's have another arrow pointing away from T. T is time, which is in seconds. So that's how you can see that watts is actually equal to joules per seconds, because E divided by T, joules divided by seconds, joules per second. Okay, so you can see that power really talks about how much energy is transferred in a certain time period. Okay, so that is our first power equation. But we also have another one called P is equal to I multiplied by V. Okay, so let's have a look at some of the equations, then we'll sort of break this down. Again, this is watts. I is in is current, which is in amps, and then V is voltage, which is in volts. Now, if we look, voltage is the the amount of energy given per unit charge, and I talks about how much charge flows in a certain time period. So can you see how P equals E over T is actually equivalent to P equals IV? Both of them talk about how much charge or energy, because remember charge has energy associated with it, which is a potential difference, or rather voltage. So these two equations end up being equivalent. Now let's have a look at the safety features present in the UK plug. The UK plug is also known as the tri or plug, and that's because it has three tri wires in it. So let's have a look at each wire in turn. So the more dangerous wire, which is why I'm going to put it in red here, is the brown wire there. So that is the live wire. So this is the wire that carries current. Okay, and so these are like brass tacks that you hear, these are squares, these are called terminals. So if you ever see that anywhere, don't get confused. Then we have our blue wire here. This is the neutral wire. And this is the wire that completes the circuit. Because remember, if the brown wire is a live wire and it's giving out current, that current also has to come right back to the plug to actually, make complete circuit. Because remember, an open circuit, an incomplete circuit cannot actually transfer any sort of current at all. Now, we also have this yellow and green wire here, which is called the earth wire. Now, the earth wire actually doesn't carry current under normal circumstances. So, does not carry current under normal circumstances. I'm going all wonky, so let's bring it down here. But when there is a fault, so say this live wire came loose and started touching the case of the appliance itself, so fault allows for current to flow out of it. And so now if the current is flowing through the earth, the casing of the appliance is no longer electrified. Okay, I hope that makes sense. Now we also have another major safety feature is the actual fuse itself, which is right here. So let's write that here, fuse. Now what does the fuse do? The fuse inside of the fuse, so let's draw a rectangle here. Remember the circuit symbol for a fuse is just a rectangle with a thin line in the middle. This line represents the thin wire that's present in a fuse. So when there is a surge. So that's a very short spike in the current flowing through the actual plug itself, such as when you turn the appliance on or off, or when there's like a power outage and very suddenly there's a huge amount of power and then there's nothing, right? So when there is a surge, the wire inside the fuse melts and the circuit is broken. Now, another thing that the fuse also does is it stops fires, because remember, if the fuse melts and the circuit is broken, that means that the huge surge in power doesn't get transferred to the appliance, and so the appliance doesn't overheat and catch fire. Now you understand the safety features present in a UK plug. Now, another type of safety feature present in UK home electrical boards is called a circuit breaker. Specifically, this is called an RCCB, a residual current circuit breaker. Now, all you need to understand about these is that these residual current circuit breakers are faster than fuses in like breaking the circuit, right? Circuit breaker, breaking the circuit. And also that unlike a fuse, which once it melts, that's irreversible, right? You have to throw that fuse away. These are only tripped. So let's put that into quotation marks, right? Which means that they can be reset. That they can be reset. So this makes them a bit more long lasting, right? Like you can constantly reset it, so every time you get like a sort of power surge, it's not the end and you have to throw it out. But however, a con of these is that they are kind of expensive. And that's all you need to understand about circuit breakers. And remember the word RCCB, because you can be asked, oh, what sort of safety feature can be used in a UK home apart from a fuse? That's a very common type of question. Alright, so let's have a look at this worked example right here. As always, we're going to highlight all of the keywords. A 2000 watt hairdryer, so straight away, that's a keyword there, 2000 watts, works on 230 volts. Oops, there's a typo there. Oh well. Calculate the rating that should be on the fuse installed on a plug. Okay, so we're talking about fuse, so we're looking at current here. So what's our power equation to do with current? That is P is equal to I times by V. As always, let's look at our units. P is in watts. Oops, watts. I is in amps. And voltage is in, well, volts. Okay, so let's rearrange this for I. So that is just P over V is equal to I. So we do 2000 watts divided by 230 volts, which gives us 8.7 amps. Sorry, I've got it on my side here. But now, do we want a fuse that's exactly 8.7 amps? No, right? Because as soon as we turn it on, the fuse will melt straight away, even though that's exactly the power that that's exactly the current that we do need for the hairdryer to actually work. So whenever you're choosing fuses, choose slightly higher amps. That's because the hairdryer itself, right, any appliance has a sort of margin of error, right? The current can fluctuate a little bit before the fuse actually melts. So rather than having an 8.7 amp fuse, let's say a 10 amp fuse. So 10 amp would be the fuse rating that we need for this hairdryer. And that would be 2 marks. Well done if you got that. Now let's have a look at the second harder worked example. A fridge is plugged into a main supply. Okay, that might be a keyword. The fridge transfers 100 kilojoules of heat energy out of it every day. Okay, those two are definitely keywords. Calculate the power of this dissipated heat energy. Okay, so we're calculating power. Now we know that there are two power equations. P is equal to IV and P is equal to E over T. Which one are we using here? Well, it says main supply, so are we talking about electricity? Well, actually, we're not, because it doesn't give us any further information about the current of the main supply. The current of the main supply can vary. We do know the voltage is 230 volts. We don't know the current, so we can just scratch off the P equals IV equation. So we have to use P equals energy transferred over time. Okay, so we have energy transferred, right? So energy transferred is always in joules, which are here in the question is 100 kilojoules. So let's convert that to normal joules. That is 100,000 joules, because 1 kilojoule is 1,000 joules. Okay, so we have that. Now we need time. Time in seconds. It says every day, so we want to convert. So we want to find out how many seconds there are in a day. Okay, so let's do that. In fact, let's do that in a different color. T is equal to seconds, and how many seconds are in there? Okay, so let's start with the smallest one. There are 60 seconds in a minute, and there are 60 minutes in an hour, and then there are 24 hours in a day. That is equal to 86,400 seconds. Okay, so now just the final step is inputting the numbers into our equation here. So we have 100,000 over 86,400, and that gives us an answer of 1.16 watts, and that is our answer right there. So this would be around 3 marks. If you understood this, well done. You're well on your way to understanding all of electrical power.